All right, I think it's time. Welcome back to everybody. I have posted the first homework assignment, which will be due on Wednesday, so check it out. It's on our class webpage, which you can get from the this thing on the syllabus right here. That's where you will find the homework assignments, and you should hand them in on Gradescope. I hope that everybody was able to connect to Gradescope. If not, let me know, and I will try and help you out. I don't know if you can tell. I had like a weird thing. I had an appointment yesterday. I had like a weird thing going on in my mouth, and so I am talking in a weird way. I actually have stitches on the top of my mouth right now, so they make me talk funny. I hope that you can understand what I'm saying, and I'll be better soon. All right, let's talk about the next thing that I want to talk about. So we have done the use substitution and the just sort of basic review stuff. Now, as far as the big list of topics, we're into like the kind of non-review stuff. I don't know if you've seen this before, but what I want to talk about, is the area between curves. This is our first sort of major non-review topic on the list. Maybe this is review for some of you, I don't know. The area between curves. What I'm talking about when I say area between curves, I mean something like, if you have two curves on a graph, maybe this is f of x, and then I have g of x down here. The area between those curves, it means, what you think it means. It's like this area here, right? Let's say from A to B, like that, right? This is what I mean when I say the area between curves. This area you can measure using an integral, right? Just like, that's how we typically measure the area of weird shapes. Now, the typical setting of the integral is just the area under a curve, just like from f of x all the way down to the x-axis. But this is the area between two curves from f of x to g of x. Maybe I'll just refresh our memory. Probably everybody remembers this, but the traditional area, the way that you measure the area using an integral is you imagine that the area was chopped up into tons of little bits, where those bits are typically rectangles. I'm going to draw some rectangles here. Now, in your Calc 1 class, you probably talked a lot about like actually adding up the area of the rectangles. We're not going to do any of that kind of a stuff here, but I just want to make sure everybody remembers that the integral is typically defined in terms of dividing the area up into rectangles, like so. I was trying to draw my rectangles on the left endpoints. Maybe you remember you can do it on the left or on the right or the midpoints or whatever. We're not going to get into any of those details this semester. But anyway, how would you find the area using those rectangles? Well, they have certain heights. Here are these heights of these rectangles are all, I will say, given by, how would you figure out the heights? Well, the heights of each rectangle is like from up here down to here. And if you want to know what actually is that y value, you would just do like the top one minus the bottom one, right? That would be the vertical distance between those two curves. So the heights of these rectangles, really they're always given by f of x minus g of x, where like in this case, f is the one on top. So this is the, you could say, the bigger minus the smaller, right? Sometimes, like if you're looking at a picture, it's always clear which one is on top and which one is on the bottom. If I just give you equations, and sometimes you have to draw the graph yourself or figure it out somehow which one is on top and which one is on bottom. But generally speaking, it's the bigger minus the smaller. And then when you do the, when you add up all of these rectangles, you get something like an integral. But it's not surprising. I will just say here, this area would be, if you wanted to really do this as an integral, I wrote B. Integral from A to B of f of x minus g of x, where f is the bigger and g is the smaller. All right, so that's the formula for the area between two curves. Not really a very complicated formula. This is the area between two curves, where you always do the bigger one minus the smaller one. All right, and that's really all there is to it. So we're going to just do a bunch of examples, sort of some simple applications of the formula, and then it can get a little more complicated depending on exactly what you're looking at. But this is the basic setup. You're just doing an integral of one thing minus the other thing. All right, let's try some. How about here is a simple one. Let's find the area bounded between x and x squared. All right. I mean the graph of those two things. So this one actually is not, there's a little bit of setup here before you just straight up do the integral, because we don't know exactly, like in this example up here, this one that I drew, I just sort of said, here's where you start and here's where you end. So that's what the A and the B are. And then by looking at the picture, you can tell which one is on top and which one is on the bottom. None of that is clear, actually, in this case. I didn't tell you where to go here to here or whatever, and I also didn't exactly tell you which one is on top. So we should look at the graph here. Now, you can always graph this on a calculator or something, although in this example, I hope that everybody knows, the graph, I'm just going to graph each of these functions. X looks like that. It's just a sort of 45-degree line. And x squared looks like a parabola opening upwards, like, not like that, like this, right? Sorry for my somewhat wobbly parabola. All right. And when you're looking at the graph, I think it becomes clear exactly what I'm talking about when I say the area bounded between x and x squared. It's that little sort of, this region right here is what I'm talking about, right? That's the area I want to find. And it also becomes clear at this point which one is the bigger and the smaller. According to the picture here, the bigger is x and the smaller is x squared, right? Bigger meaning like farther up in the y direction, in the vertical direction. Okay, so when I do my integral, it's going to be the integral of x minus x squared, right? It's always the bigger minus the smaller. The other question is, what about the two endpoints, right? The a and the b in the integral, they should be here up to here. Those are the a and the b. And you have to figure out what those points are. Now, I can tell the one on the left is 0, right? This is x equals 0. What about the one on the right? This one you have to just sort of figure out. Anybody think you know? What actually is this point where the two lines cross? Yeah, what do you say? 1. Yeah, how is that what you said? How would you, no, oh, okay. I can't hear very well either. Anybody agree that it's 1? How do you know that?
1, as we put in for x, is just 1, and 1 squared is also 1.
Yeah, right. What you're looking for in terms of this I can't say that word, intersection, is when are these two functions going to have the same value, right? When are the two y values going to be equal? And it's 1, because 1 is the same as 1 squared. And also 0, it's the same as 0 squared. But there are no other numbers where those are equal. Now, if you don't want to think that through, and actually I would recommend, like, here you can kind of figure it out by some sort of common sense, but I don't want to rely on that generally. So to find the endpoints are at the intersections where those two graphs meet. And I hope you remember how to find the intersection of two graphs would be you set the two equations equal to each other and then solve for x. So that in this problem would look like this. X equals x squared, and you solve for x. All right. You may be tempted to divide both sides by x, which is not entirely wrong, although you miss out on one of the solutions. So the proper way to solve this would be to move everything over to one side. So I'll write it as 0 equals x squared minus x. and then factor. X minus 1. And this means x equals 0, x equal 1. Those are my two intersections. So even if you didn't know what the picture looks like, this is how you would kind of work out the details. And most of the time when you're doing these on the homework or something, you're not always going to know what the picture looks like. So it's a good idea to be able to do this, even though in this particular example it's not so hard. All right, anyway, the endpoints here are 0 and 1. All of this is the setup to let you set this whole area thing as an integral. So remember, the formula is right here. Not too hard of a formula to remember. So I'm going to do, so now I can finally make this as an integral. The a and the b are 0 and 1. And then I go bigger minus smaller. Biggie minus smalls, if you will, which in this case would be x minus x squared, right? X is the bigger, x squared is the smaller, according to the picture. Right? And now this is just an ordinary area, or an ordinary integral, which you can just work out. So let's just do the integral then. So I do the antiderivative. Now sometimes, you know, you might have to do some fancy tricks. You might have to do u substitution or something like this to finish it off, although in this example you don't. I go, the integral of x is 1/2 x squared. The integral of x squared is 1/3 x cubed. And then I'm going to plug in 0 and 1. So it's 1/2 1 squared minus 1/3 1 cubed minus, and then plug in 0. 1/2 0 squared minus 1/3 0 cubed. That's it. Really, all these zeros are 0, all these ones are 1, so it's 1/2 minus 1/3, which is 1/6. Although, as usual, I don't really care if you simplify it like that, but this is the answer, which to me looks about right. I mean, that area is, on the picture at least, you know, it's not a very big area, right? Any thoughts about that one? This is a fairly, I would say, fairly basic one. It can get a little more complicated, but you got to start somewhere, right? All right, let's try another. So there are a few different kind of variations that can make this slightly more complicated, but that, you know, what we just did, that's the basic idea. How about, oftentimes you will see a picture. How about just find the shaded area? And here's my picture. You don't have to draw this exactly perfectly like I do. Okay, one of the curves is y equals -x, which looks like that. So I can draw that fairly perfectly. Should go through the origin. There we are. Okay, so this is y equals -x. And the other one is another line, 2x plus 1. So it goes, the intercept is here, and it goes something like this. This is y equals 2x plus 1. And the shaded area I'm referring to is going to be here and here. So this and this. Right? This kind of bow tie type shape is the shaded area. Where this, I guess I didn't label it. On the x-axis, this point here is 2. All right. So actually, this example, like one thing that's easier about it is I just straight up told you what the two endpoints are, like the a and the b. It's going from -3 on the left and 2 on the right. Although, unfortunately, in this case, you cannot just do those as the a and the b. Not exactly, because here, what's more complicated about this one? I'll say we need to consider the crossing. The reason the crossing sort of makes things a little weird is because if you look at this thing overall, there is no bigger versus smaller, because like on the left side, the y equals -x is bigger, but on the right side, the other one is bigger. So you can't just set it up as one single integral. We have to break this into 2 parts. So we're going to do 2 separate integrals for, you know, this side and this side, right? You have to do it separately because the bigger versus smaller changes from one to the other. And so if you can't just do it as one whole integral across the whole range. All right? Okay, not such a big deal. That means let's consider the one on the left first. So that would be this triangle. We're going to start integrating from -3 and go up to this point. Now we need to determine what that point is in order to set up these integrals. So we have to find this point here. This is find the crossing point. On the left-hand shape, we're going to start at x equals -3, but we are not, at this point, we don't really know where we go up to. All right, but anyway, how do you find the crossing point? It's the same as the previous example. You set the two equations equal to one another and then solve for x. So in this case, the two formulas are -x and 2x plus 1. So I set these equal to each other and then solve for x. I would solve for x by maybe, put all the x on one side. So let's subtract the 2x over onto the other side. So it'll say -3x equals 1. And then divide by -3. And it says x equals -1/3. All right? So that's where that point is. Now I think we have all the necessary sort of ingredients to set this thing up. So let's try it out. So let's do this part first. The area here will be it's the integral, right? -3 to -1/3. That's because you can see the picture. The leftmost side is at x equals -3, and then you go up until you hit the crossing point. And then inside the integral, I go bigger minus smaller, right? The bigger function. And on the left side of the picture, the bigger function is here, which is -x, minus the smaller function, which is the other one, 2x plus 1. Make sure you put parentheses here because the minus sign is going to get distributed. Right? And it's gonna matter. You could just do the integral directly. I think I would like to simplify a little. Like you can actually recombine the terms inside of there before doing the integral. So this is -3 to 1/3, -x. Let's distribute the minus sign. -x minus 2x minus 1. And then you can add up the x's. Sorry, it's -1/3 at the top there. Add up the x's. It says -3x minus 1. Now that's as simple as it's going to get, and we can do the integral. So you do the usual thing with the exponents. I'm going to get -3 over 2x squared minus 1 becomes just x. Remember, a constant by itself inside the integral becomes whatever that constant times x. Right? And then we're going to plug in the two values, -3. Well, -1/3 first, and then subtract and plug in -3. So here I get -3/2 -1/3 squared minus -1/3. All right, that was plugging in -1/3, and then I go minus, plug in the other numbers, -3/2, -3 squared minus -3. There you go. This is my answer. This is not the final answer. This is just the area of the one on the left, right? Now we should do a similar thing to find the area of the one on the right. So the other one, which is this one here. Can anybody say what's the boundaries for my integral this time? Look back at the picture. Yeah. -1/3 to 2. I like that because the region on the right here, it goes from this crossing point, which is x equals -1/3, all the way up to this x value, which is 2, just because I said so on the picture. Excellent. All right. And now I go bigger function minus the smaller function. On this part of the picture, the bigger function is this one, 2x plus 1. So this time when I do the integral, it's 2x plus 1. That's the bigger, minus x. Minus negative x, right? That's the smaller. Make sure you get all your minus signs in there. Yes?
Can you just explain quickly how you know what's the smaller one?
Yeah, it's this you can tell by looking at the picture. So if you're just looking at this part, the bigger is sort of the I'm always talking about the distance between two lines. And by bigger, I mean just like the one which is on top. And smaller is the one which is on the bottom. Bigger and smaller meaning the y values of this function are bigger than the y value functions of this, or the y values of the other one. Yeah. Great. So there it is. Now we can just do the integral, and it's not a hard integral to do. So I am again going to try and simplify before integrating, just because I like that. Minus x turns into plus x, and then this can add on to the other x. So there's already a 2x. I'm going to add another x. 3x plus 1. Because I had the minus x. All right. And then do the integral. 3/2 x squared plus 1/2 x, and we plug in 2 and negative a third. Plugging in here, I get 3/2 times 2 squared plus 1/2 times 2 minus 3/2 times negative a third squared plus 1/2 times negative a third. And that's that. All right. This is not really a hard integral to do once you set everything up correctly. Yes?
When you did the integral, how did you get 1/2 x?
Oh, that's wrong. Sorry. I don't know why I said that. 1 it should be just x, right? Is that what you thought? Yeah. Thank you for that. Sorry about that. Take out all those 1/2s. I don't know what I was thinking. Like that. Now are you happy? Yes. Okay, good. You will notice I'm actually not terribly good like with numbers in general, so I'm prone to mess these things up. Please let me know, and I appreciate it. All right, excellent. We should just say so what is actually the answer to this big problem here? Remember the question was finding this total shaded area. So I haven't actually written down what exactly is the answer. Maybe I'll just say, and it's kind of a pain to write this just because I wasn't actually calculating any of these numbers. But can I just say the total area is, this thing plus this thing. Would you mind if I just leave it at that? And if you're doing one of these problems on the homework or something, it's totally fine with me if you want to write your answer like that. Or you could plug all these numbers into your calculator if you want to and add them together. But this is our total area. All right, any thoughts about that one? I have some for you all to try, but actually I have one more variation. So this one that we just did was a slight complication because you had to break it into two pieces and figure out where this intersection point is to break it up. One more complication that could happen. So here's one which is not crossing, but I will say sometimes you need to, I'm gonna call it, do it sideways. You'll see what I mean in a moment. How about, let's find the area between y equals 1/2 x and x equals y squared minus 3. You can immediately tell this is going to be a little weird because I wrote the second one there is not actually a traditional function. It's got x in terms of y rather than the other way around. Anyway, let's draw a picture of this. So y equals 1/2 x is no problem. I mean, that's not really weird at all. It looks something like that. The other one though, x equals y squared minus 3. This is kind of a sideways parabola. It looks like it's a quadratic thing, but it's y in terms of x rather than what we usually do, x in terms of y. What that one looks like is this. So coming back to 3 here, and it looks like a parabola that goes this way. So maybe I'll try and sort of extend these out. All right. And the area between these two things, this label is not very helpful anymore. Sorry. Put it down here. So this other one is x equal y squared minus 3. And the area I'm talking about is this area here, right? I say do it sideways. What I mean by do it sideways is if you try to do this, don't write this down because this is not the correct way to think about this problem. But if you try to do it in the traditional way that we've been doing, the idea behind it all, remember, was you would sort of imagine little rectangles here. And those rectangles, they stretch from the top function down to the bottom function. And actually, the rectangles that I drew are actually totally fine. The problem is, if you try to do that for the entire area, that one's fine, that one's fine. But eventually you get over here to this, and this is sort of not fine. What's different about that rectangle is it doesn't go from the top function to the other function. It actually goes between two values of the same function. And this is not, it's not gonna be possible to use our formula about like f of x minus g of x in this case. Because what are you gonna do? Like, you're going to do g of x minus g of x again. That's 0, but this area is not 0. So it's not going to work to do it this way. What I said before, do it sideways. What I mean by that is instead of thinking about those rectangles, what I mean by do it sideways is do rectangles like this. If you draw the rectangles this way, actually now, all the way down, they always go from the line over to the parabola part, right? There is no place in which you have a rectangle connecting sort of two pieces of the same curve, all right? Do it sideways. What that really means, or how do you actually do it sideways? The idea is, this is maybe easier than it sounds, you just rewrite everything as x in terms of y, rather than y in terms of x. This is what it means to do it sideways. You just imagine that you interchange the roles of x and y throughout the whole thing. Rewrite everything as x in terms of y, rather than y in terms of x, all right? And of the two functions I gave you, actually one of them is already like that. So this one right here, I'm just gonna leave that as is. I feel good about that already. Let me just add into my suggestion here. Do the integral all as y values with a dy. You'll see what I mean. All right. So I want to write my two equations rather than y equals something or other. I'm going to write them as x equals whatever. And one of them is already like that. X equals y cubed minus 3. And the other one, we can put it into that format by just solving for x instead of y. In this case, it's very easy. You would multiply both sides by 2 to solve for x. It'll say x equals 2y, right? Those are now my two functions. They're functions of y instead of functions of x, but we can do all the same stuff with them that we did before. All right? And so my integration, well, the other thing we need to consider is what are the boundary values going to be on the integral? And you do not want boundary values of x, you want boundary values of y, because I'm trying to do the whole thing in terms of the y values. So here are the intersections, and then my a and the b in the integral will be here and here. They are y values because I'm trying to do everything in terms of y values instead of x values. And how would we find those two values? Anyone got a suggestion? Yeah?
Set them equal to each other and solve for y.
Yeah, set the two equations equal to each other, as we usually do. This is, again, just finding intersection points of two equations. So I am going to take these So we're going to find the intersections by setting them equal to each other. Hopefully this will work out. Now they're both already solved for x, so I could just say y squared minus 3 equals 2y. Anybody know how to solve this? Yeah?
Subtract 2y and factor.
Yeah, subtract 2y and then factor, she said. I like that. So it'll say y minus 2y minus 3 equals 0. And then factor on the left side. Any factoring masters out there? Factoring, of course, means, you know, this thing. What do you think?
I got y minus 3 and y plus 1.
Y minus 3, y plus 1. Yeah, I like that. Y minus 3 and y plus 1. Remember, when you're doing this factoring, these two numbers, their product is that. They have to add. They have to multiply to be this number, and they have to add up to be the number in the middle, which is, it works. All right, and then after doing this, you know, to finish, you split it up. Y minus 3 equals 0, y plus 1 equals 0, and then you solve each one. Y equals 3, y equals negative 1. And that actually looks reasonable on the picture, right? So the A here we have determined is negative 1, and the B up top is 3. Right? This point, which I labeled 3 in red, is totally irrelevant in this approach, because we are not considering the x values for our boundaries. And anyway, it's negative 3 over there, but it doesn't matter. That's a red herring. Okay, I think we're actually ready to set up the integral then. So my area is, somehow I got onto blue pen. The integral of something to something, and this. The boundary values here will be minus 1 to 3. That's the range of y values that we're considering when we do the integral. And then I go bigger minus the smaller. And you have to be a little careful about what exactly that means in this case. Bigger minus the smaller means bigger x value minus the smaller x value. So between these two functions, I have this straight line and the curvy curve. Which one is the bigger in this case? Meaning bigger x value? Any other ideas? The bigger x values, that would be, on this picture, bigger x value would be further to the right, right? These all have, like, over here, this x value is greater than that x value. So when I say bigger on one of these sideways ones, it means the one that's further to the right. So in this case, it's the line. So I go bigger minus the smaller. The line was 2y minus the smaller was the parabola. All right, this is bigger, this is smaller. By bigger, in this context, we mean further to the right, and smaller means further to the left. Right. When you're doing an ordinary one with, and I'm going to put a dy here, my variable is dy. When you're doing like an ordinary dx integral, bigger means higher up. When you're doing this dy style, it means further to the right. Okay, and now we've all set everything up. From now, it's a fairly straightforward to finish the integral. Let's just do it real quick. I go minus 1 to 3, just to simplify a little bit. 2y minus y squared plus 3. Make sure you put those parentheses when you subtract it so that you get the signs right. And then we just do the antiderivatives. So I go 2y becomes just y squared minus 1/3 y cubed plus 3y. And I'm plugging in 3 and minus 1. So we end up with 3 squared minus 1/2 times 3 cubed plus 3 times 3 minus all this, but with negative 1 plugged in. Minus 1 squared minus 1/3 minus 1 cubed plus 3 times minus 1. There you go. All right, this is similar but kind of sideways, like I said. All right, any questions about that one? Now I have some for you all to try. I got 2 for you. See what you think. In each case, your job is to find the shaded area. How about this has a line and also a parabola. Ooh, look at that. I didn't know I could do that. Get a nice, that's not actually a parabola though. It's like just some weird curve. All right, anyway, something like that. Do that? Huh. All right. Okay, here the shaded area I'm talking about is this and also this. So this one you're gonna have to like break it up somehow into 2 bits. I'll tell you the formulas though. This line is y equals 3 minus x. The parabola is y equals 3x minus x squared. All right. So that's the first one. The second one. These will each take you, several minutes to do. So we'll have some time. All right, see what you think. Feel free to chat with your friends about it, and I'm gonna walk around and see how everybody's doing. Please let me know if something's not making sense. I would be happy to refresh your memory.
further, since the
Well,
3
you
is
would have to
further,
choose one.
like further
Just
along the
like
x-axis
this.
than 1, would my 3 be
For this one,
my
or
one
Yeah,
way?
that's right.
Yeah, I just have a question. Can you simplify like this?
No, that's.
Like that's
Oh, yeah. Yeah. Or you could do it directly here, but I would. Okay.
good here.
There's this one more.
Okay. Sorry, I had a typo in the second one. This is y squared plus 1. Sorry. Like y, just straight up y squared would go through the origin, but I didn't mean for that. Does that change anything? Oh, I did mean it. I just drew the picture wrong. Sorry. I mean, it doesn't make a big difference either way. Let's keep it the way I said. But then my picture is not right. That parabola should go through the origin. Sorry. None of this really matters about how you actually do this problem, but like so. Now do you feel better? No, it doesn't really matter. Okay, now you set formulas equal to each other when you're looking for inspection.
Yeah.
They don't intersect.
Right.
So you have to somehow figure out, like, what you're looking for is where is the lower limit and where's the upper limit. Like, that's the only reason you can get those intersections anyway.
No.
But you can just tell me what you have to do in this case. In terms of the y values, the lower one is 0. That's right on the x-axis, and then I think you should be able to figure out what that is.
It would have been 1 because x plus 1 is shifted on right.
Yeah, when you did this. Yeah. Oh, okay.
How's it going? can we talk about these? I see pretty much everybody worked their way through the first one. The second one is a little tricky, but let me just say the first one, just because I've seen everybody worked it out, you should start by finding these intersection points, and they are 1 and 3. If you work this out, this comes from setting the two formulas equal to one another. And then so the region on the left side shall be set up like the integral from 0 to 1. That's because the leftmost side of this is at x equals 0. So the leftmost part is the integral 0 to 1, and then I go the bigger one minus the smaller one, and on the left side the bigger one is 3 minus x. So this should look like 3 minus x minus the smaller function, which is the parabola part, 3x minus x squared dx. And then this, you do this integral and you get something. All right, that's the left side, and then the right side is, so maybe I'll get my colors going here. The right side here is similar, but it now is going from 1 to 3, and this time the bigger and the smaller are reversed. So the bigger function on the right side is 3x minus x squared. Subtract the smaller function is 3 minus x dx. And then you do this integral. I don't know if I need to go through all the details, just because I think everybody worked out eventually. Anybody got questions about that one? I hope this one worked out for you. Make sure you put the parentheses in here. I know there's, I don't know if you've ever met them, but there are out there parentheses haters. Parentheses haters may screw up the signs. Here you need to distribute the minus sign. Yes, are you a parentheses hater?
No.
No, all right, great.
Do you ever want us to like simplify our answers? Or just like
Basically, no. I mean, I would expect you to do more than just this. Like actually do the integral, but then you can get yourself down to say something like this, you can leave it at that. Yeah. If you're ever unsure on a test or quiz or something, by all means ask me, is this good enough? And I will say, probably, yes, it's good enough. All right, great. So let's talk about the second one. I think the second one is a little harder just because this is one of those somewhat weird sideways ones, right? So if you were thinking of the rectangles, in this one, they sort of go this way, although I don't necessarily think it's helpful to think in terms of the rectangles, but that's what we're doing. You want to write everything in terms of x as a function of y. So this one, x equals y squared, is already the way I want it to be. The other one, you should solve it for x in terms of y, and it will say x equals y minus 1. That's how you would solve for x in the other one. All right. I saw a lot of people were just kind of like mechanically setting these equations equal to one another to find the intersections, but in this case, actually, that's not appropriate because those two curves don't intersect. The straight line here does not have intersections with the parabola part, so you're not even going to get anything if you try to set them equal to each other. It's not necessary. You can just begin writing your integral. So maybe I'll move this guy down. You can just immediately set up the integral. Integral from something to something of the bigger minus the smaller. That's how we always do this. Can anybody say in this example what's the bigger and what's the smaller? Yeah. The parabola is the bigger. Yeah, when you're doing them in terms of y, bigger means further to the right. Bigger meaning bigger x value versus smaller x value meaning further to the left. So my inside the integral is going to be y squared minus y minus 1 dy. And what about the integration boundaries? That is, what is the range of y values which make up this area? And this area, of course, is here, right? And what is the range of y values? That means sort of from down at the bottom up to the top. What are the y values that I'm considering? You can tell by looking at the picture that the bottom here is at y equals 0. So this, where the bottom is at y equals 0. So I'm going to put a 0 there. And then it goes up to however high up that is, right? How can you tell where that is on this picture? It's not an intersection of the two curves, so you don't find that point in that way. You could say this point, though, it is the y-intercept of this line, right? And that you can tell just by looking at this formula. The y-intercept is 1, because this is in the old, mx plus b format. The 1 should be the y-intercept here. So that top of this area is at y equals 1, and that's why I put a 1 up top. So this is the setup. These kinds of problems, and actually this is the case in a lot of the ones we're going to be doing over the first few weeks, often the setup is the hard part, and then once you have it set up, it's a fairly straightforward to do the integration. Here I would, let's just finish this one off. 0 to 1, y squared. I will distribute the minus sign and then actually do the integral. It's going to be 1/3 y cubed minus 1/2 y squared plus y. Plugging in 0 and 1. I hope everybody is feeling good about doing basic antiderivatives like that. And then we plug in 1, and then we subtract, and we plug in 0. So it's going to be 1/3 1 cubed minus 1/2 1 squared plus 1. Subtract all zeros. This is all just going to be 0. Like that. There you go. I think this is 1/3 minus 1/2 is negative 1/6. I think this is 5/6 if you simplify it out, although I don't really care about that. All right. Certainly the answer should be positive, right? It represents this area. So if you ever do plug these into your calculator and you get a negative number or something like 0, it means you probably messed up the calculation at some point. All right. Anybody want to chat some more about those? We got a little more than 10 minutes. I think that's enough to start talking about our next bit, but this is the end of what's going to be on the homework. So you should be able to check out the assignment, and in theory, you should be able to do all those problems tonight. I've heard that that's how you young people like to spend your Friday nights, doing calculus problems. I've been there, man. I was your age once. All right, let's talk about the next section, just a little introduction since we got 10 minutes or so. This is another using the integral to find, to measure weird shapes, but this time I want to talk about volumes using the integral. All right, and this type of application of the integral, this is often called volumes of revolution. That is, these are going to be volumes. You can use the integral to find certain types of volumes of shapes. In particular, we're going to talk about volumes of revolution type shapes. What I mean by that is, if I have let's just say I have a function here. Maybe looks something like that. As usual, I'm just going to consider like a little bit of it from A to B, say. Now, the typical use of the integral would be to find the area under that curve. But you can also use the integral to measure other kinds of weird things. And what I'm going to talk about is the volume if you rotate that curve around the x-axis. And this is called the volume of revolution. So what you have to imagine what I'm talking about here. I mean, you take this whole shape and sort of spin it around the x-axis, and it makes this kind of a lampshade type shape. All right, this is a three-dimensional volume which is obtained by spinning that curve around the x-axis. All right, and I would like to find the volume of this. All right, there is a formula for this, which is, I suppose, slightly complicated, but not really all that complicated, which in the next 10 minutes, I will explain to you what the formula is, and then we'll do some real examples next time. I want to find the volume of that shape, though. All right, so the basic idea here, just like the idea behind all integrals, is we are going to imagine cutting this shape up into a bunch of little bits. Now, they're not going to be rectangles, because this is now a three-dimensional shape, but I'm still going to imagine slice up the shape vertically. Ordinarily, these, when I slice it like that, right? That's what I'm talking about here. slice the shape like that. Can anybody say, in terms of this three-dimensional shape, if you make those kinds of cuts and then like look at each chunk that you get, what kind of a shape do the pieces look like? Yeah. They look like cylinders. Yeah. Some people would describe these as like discs. That's like a very thin, round thing, right? It's kind of like a circle that you could sort of pull out of this thing. Although, so I would say slice it up vertically. Each piece to me, if you were to sort of grab one of these slices and hold it in your hand, I would say each piece kind of looks like a circle with some very thin amount of thickness. That makes sense to say? A thin amount of thickness, all right? It's a circle with some kind of little thickness to it. That's another thing I know about the young people today. They like the thickness. Each of these circles has a little bit of thickness to it. What I said, I asked a moment ago, she said, I said, what kind of a shape is this? She said, it's a cylinder. This is, usually when people say cylinder, they imagine sort of a tall and skinny shape. But actually, this really is a cylinder. It's drawn sort of sideways, and the tall, it's not tall and skinny. It's got the thickness, right? It has a very short. This is what we usually call the height of the cylinder. This is a cylinder with a very small height, and it's sideways, all right? But anyway, this is a cylinder. It has a certain radius and a certain height, which I'll write that way. And maybe I'll call the radius R and the height. Just for fun, would you mind if I call the height, which is drawn horizontally in this case, I'm going to call that delta x, because I imagine that like this sort of thickness to it comes from all these little bitty slices. And when we're doing the integral, the width of each of those slices, we call it delta x. And so when you pull out one of these things, it has a certain width, which is given by this delta x, and then it has a certain radius, all right? Can anyone suggest where does the radius come from in terms of the original picture? What about the picture determines the radius? I already said the thickness of this is really the width of each of these little rectangles. Can you say where does the radius come from on the original picture? Yeah? Yeah, it's like the height of this function, right? The radius would be the distance measured from the middle up to the curve. In other words, that's just the y value along the curve, right? So here, the radius of these cylinders, this radius is just the y values of the curve. If you think about where that sort of disc-shaped thing came from on the original curve, that radius was determined by the height of the function at various points, all right? So we could say, like generally speaking, R is just kind of like f of x, right? The y value, how do you find the y value? That's what f of x means, y equals f of x, right? What I want to do, ideally, to find the total volume of this weird revolved shape would involve adding up all the volumes of these little bitty bits, which look like this. So each bit here, I would like to talk about the volume of each bit. Each bit has volume. Actually, maybe we should refresh our memory about a little something about the volume of a cylinder. Does anybody remember, like the standard way we draw a cylinder is over here. It has a radius, which I'll call R, and it also has a height, which I'll call H. Anybody happen to remember the volume of a cylinder? There's a formula for that. I don't really care if you do remember this or not. Do you actually remember this? It has a radius and a height. The volume is actually equal to the area of the circle part times the height. Makes some kind of sense to me. And the area of the circle part, of course, is pi r squared. So the volume, this is the formula for the volume of a cylinder. I don't really care if you remember that formula. But using that formula on the shape on the right, each bit in this case will have volume pi times r squared, but I'm going to write that as f of x squared because the r on my little disk over there is determined by the f of x, and then times the height, which is delta x, which looks like a width over there. All right. And so to find the volume of the revolved shape, we are going to add up all these bits of volume. All right, if you wanted to estimate this, it makes something like a Riemann sum. You know, that's when you add up all the rectangles to measure the area. But of course, we don't, in this class at least, we're never going to actually calculate the Riemann sums by adding up little rectangles. We're going to do it by doing an integral. So if you translate this into an integral, so we add up all these bits of volume, as a Riemann sum, it looks like, you know, some kind of summation of pi times f of x squared times delta x. Those kind of sums you basically never want to do in real life. This becomes, though, the integral. And this, I'm finally getting to the formula here. Remember when you turn a Riemann sum into the integral, the delta x sort of goes away or becomes dx in the integral, and then the rest of the stuff in the sum becomes the stuff that you are integrating. All right? We got 2 more minutes, so that's plenty of time to finish. So this is basically the formula for the volume of one of these revolved shapes. I should say, what about the 2 boundary values for this integral? That would just be, you know, I'm slicing this up as I move from left to right, starting at A and going up to B. So that's what you put in the boundary values of the integral, A to B. All right? And this is the formula for the volume of revolution. Now, when I write this formula typically, pi, of course, is a constant multiple inside, and you can factor it out of the integral. And you basically, you always might as well do that. So this is the big formula, which I'm going to put in a box. And this formula, I suppose you should memorize eventually, although hopefully you're going to do enough examples that you're not going to ever have to sort of sit down and consciously memorize that. But this is the formula. So this is for volume of revolution. All right. That, again, ends up being a fairly simple formula to work with. So just like the area between curves stuff, when you're doing these volume of revolution problems, usually the hard part is setting it up to begin with. Once you eventually decide all the ingredients, you plug them into the formula and everything works out just fine. All right, I think we'll leave it at that. So the homework will not include this volume of revolution stuff. We'll do more examples next time. Please check out the homeworks and let me know. You know, it's due on Wednesday, like Wednesday before midnight. So you have plenty of time to work it out, but I'd be happy to chat about it. All right, have a good weekend.